So today we will be looking at presentation of the paper by Mikael Hanoff and our lecturers Alfredo Canciani and Jan LeCun. So that's their work from 2018, I guess, and it's like a pretty interesting paper called Model Predictive Policy Learning with Uncertainty Regularization for Driving in Dense Traffic. So as you can guess from the name, it's not like quite regular deep learning paper. It kind of combines a bunch of stuff together, so that would be really interesting to look into it. So let's start. And first, let's try to kind of take this name of the paper part by part and understand what each part of that means and stands for. So first of all, we will be talking now about model-based learning. And so what does it mean in this case? So in general, we have an agent. So this is something hopefully intelligent, which makes some decisions and does actions. And these actions interact with a world, and the world outputs some cost and a state. And again, agent will look at the state it is now and output the next action and so on. So if we don't have a model, our actions, so our agent will rely on kind of samples of the real consequences of the actions, right? But that might be not great for some cases, and particularly when like in this example, the cost of mistake, like even a single wrong action may lead to bad consequences because we consider like autonomous driving here, and you probably don't want to break too many cars when driving, when learning how to drive. So we move to the model-based learning. In this case, we use a model to output states and cost for us to learn from. And this model basically will provide us with similar kind of information as we would expect from the world, right? So we want this model to provide us with the same kind of distribution of possible future states and costs as the real world would do. Okay, so how would the learning, how would we create such a model? So basically this is kind of straightforward. Here is this scheme. We input an action and we have some state. We are at some state at time t0. And we start from that state, and we let this, like we observe the real world, and it outputs a sequence of states S sub t, and costs C sub t. And here we use mean squared error to learn to, our model should output the same sequence of states and costs as the world would. So this is basically standard supervised training, right? So everyone probably is familiar with this kind of framework. So actually, what we do here, we do not learn these costs, and they treat it a bit different way, but we only learn to output the states. So our model will predict the state to which we transfer from previous state given an action at this point of time. Okay. Okay, so let's so that was abstract, and now let's consider this example. So the real world in this case is like a video captured by a camera at some roof of the building, right? And it films a traffic. And here you can see there is a bunch of cars, and we just film those cars from above. Then we align these video frames and find the bounding boxes for each car, and form this kind of like a map, which is it's not a real world, right? But it includes like a mapping from these cars to some like 2D plane here, and from this we will get following information. We can get from this velocity and position of each car, and in this case, action is acceleration of each car, and we can. These are videos, so and we know basically the kinematic model of the car, so we can like reverse this kinematic model and kind of extract the actions, so the accelerations from this video, right? Because if you know where the car was at like previous moment and in the next moment, so you can get velocities and accelerations from it, as well as position. Okay, so and then this kind of this is a general picture of the road here, but we are interested in state which would be like relevant to each individual car. So here we can you can see here we like cut this bit from the total picture, and we turn it into this representation of the surrounding of the car. So here the blue car is like our agent, yeah, and green cars and these lines here are basically a part of a state. So position, velocity, and surrounding of the car represented as this picture here will form our state here, and accelerations would be our actions. Okay. Now we want to basically evaluate. We need to get some kind of cost signal to distinguish between good and bad states, right? So what is a good state in this case? We want to drive within a lane. This is like a first condition, and we want to be at a safe distance from other cars. So the first part of the cost, which is lane cost, here you can see you can see this function here, and if we are centered with respect to the lane, then the cost would be 0. And as we shift towards the sides of the lane, the cost grows linearly, and it's symmetrical as we don't want to go either to the left or to the right from the center. Okay, so that's one component. And the second component is proximity cost. So proximity cost, it has kind of two subcomponents, like Y and X component. And basically, we don't want to have any car like just in front of us. And we care less for those cars which are kind of shifted to the side. And also we want to keep this distance from other cars. And this component depends on the velocity. So the higher velocity, the longer distance we want to keep from other cars, because it's kind of, probably understand, it's more dangerous to be closer to the cars when you travel with high velocity. All right. And so this cost here, it can be represented as this kind of blob, and we can multiply this. You can view it as a matrix, right? And this is another matrix. And it's basically kind of a binary matrix. It has 3 channels, and here we take a green channel, and we multiply it by this matrix here. And what it gives us, if we have some cars within this safe region, we can say, then we will get like non-zero number from this multiplication. All right. And so what's good about this formulation is that we get a differentiable cost function for proximity cost. And here, in this example, we can see what is the difference between, like, if we travel at 20 kilometers per hour or 50 kilometers per hour. And if we travel at 50, like, faster, then we have like this wider region, which will result in some non-negative cost, right? And if we travel at low velocity, this region is smaller. Okay. So the plan for what we will, like, consider today. So first we need to learn the world model, which will kind of mimic the real world and output the states. Like basically it is responsible for outputting like transitions from state, from previous state to the next state, given some action. The agent is supposed to plan how do we interact with the world. It has like it interacts with this model, and given and it kind of should produce the action which will result in desired state. And finally, we want to evaluate our agent by interacting with the world. Right. So, and here the first step is a world model. All right, and the world model here, basically what it does, we input a sequence of states from 1 to t and action at time t, and it outputs a next state. So that is a prediction of our model. And a target for training this model would be an observed state from real world data. So here the state is pt, which is a position, velocity t at time t, and this kind of pictorial representation of our state, right? And this is we have this from the videos from the real world data, right? And we can train the world model on it. So okay, so the first kind of thing they considered is deterministic predictor decoder model. Okay, so basically this predictor, it takes action A and states from 1 to T and outputs some hidden representation. And then decoder maps this hidden representation to the next state. And then we can compute mean squared error, comparing like actual state from the real world and our predicted state, right? So this is like standard supervised training framework, right? So what the problem is with this approach? And the problem here is that this kind of model outputs a blurry prediction. And why does this happen? Because actually we do not have a single correct prediction for the next state. Like let's consider this picture here. Probably we can predict that each car here will move with some velocity forward, but we cannot certainly predict the velocity for each car. We cannot deterministically define if what would be the acceleration. Maybe this car will go kind of faster ahead because it has some free space, or maybe this is like a newbie driver and he doesn't want to speed up and he will drive carefully, right? So both scenarios are valid, and basically our deterministic encoder decoder, it kind of the best thing it can do, it can output some kind of probability distribution of a possible future state. And as we go further into the future, the predictions became more and more blurry. And if you watched the video lecture, you saw that, I think within 10 seconds, the picture becomes really blurry. And yeah, so the example Alfonso gives us is that if you place a pencil on its tip, you cannot predict where would it fall. So the best prediction you can give would be kind of some kind of blurry distribution, because each direction of falling is equiprobable. And yeah, another example of multimodal behavior I found really helpful. Imagine like a drone flying, and we have a tree, and it and we want to imitate, we have the data from a human pilot, and we want to imitate it, and not to hit the tree, the pilot can go either left or right, and it's possible that it will take each action with equal probability, right? And in this case, an average prediction would be go to the tree, right? And that's not really a good prediction. And we need to resolve this multimodal behavior somehow. We want to get a single modality, and one way we can do it is by using a latent variable. So we introduce here latent variable z, and this latent variable is basically connected to our actual next state. And this actual next state it goes through some encoder, which outputs expectation and variance of Z, and then we sample Z from this posterior distribution, output by encoder, and we regularize this encoder by introducing this KL divergence term with a prior distribution, which in this case is like a normal distribution with diagonal covariance matrix. And okay, so this helps us to resolve this ambiguity. Basically, given this encoding of current state and action, we cannot output a single prediction here. But using this variable Z, we can kind of resolve this ambiguity, and by taking this Z into account, we have like a single correct prediction corresponding to the real next state. And then at the inference time, we can use this posterior distribution to sample from it and to get again, to get a concrete, not blurry predictions, right? So yeah, this is an inference time, and we do not have like actual state T+1 from real world, but now we still have this posterior distribution learned during training, and we can sample from it. And here is some kind of mapping to match the dimensionality of the predicted hidden state and Z, because we want some kind of low dimensional latent variable, but to sum those two, we need to apply some mapping to it to match the output of the this predictor. Okay, so and here is kind of the first frame. so you need to watch the video to see the difference here, and actually what it is. Yeah, maybe I'm not sure if we want to watch a video right now. Do you guys want to watch a video, or you probably watched it, or you can watch it after, if that's okay?
There is a animation too on the link I have just shared.
Oh, okay, let me get the link. That's great. Okay.
It's on the chart.
Yeah. Okay. Okay, can you see my screen with this animation? You shouldn't see animation yet, but yeah, it's still loading. Let's check out.
Yep, here.
Okay, yeah. Yeah, so here we got this, and yeah, it's still loading. We should kind of wait a bit, but yeah, this animation has loaded already, and here you can see that maybe just scroll in a bit. That this second one from deterministic predictor encoder, predictor decoder, whatever, it becomes blurry with time, but this outputs from the model with latent variable, those remain kind of exact, right? So we have some concrete states. And if you watch carefully, you can see that there are multiple possible predictions but by using this latent variable, we can actually like have a single prediction for each kind of, basically each correspond to some possible future, right? Okay, so let's get back to our presentation here. So we watched, so, and basically what he shows that there are two cars which can travel with different speed, but in all these four cases, those remain like a concrete car versus like a blurry distribution of possible position for this car here. Right. Okay, so and I think at this point we are ready to go and check out some code for this. So first, let's look at the training code for this. It's called train FM, and FM stands for forward model here, right? And yeah, so this is a script, and basically the training function is this one. It's not really a big function here. And what do? We set model to training mode. We have three kinds of losses. So here is like image loss, state loss, and this one corresponds to the like difference between predicted images from the total state, and this one corresponds to difference in predicted position and velocity. And the third component corresponds to this KL divergence term for variational autoencoder in case if we use it. So basically we can use either deterministic predictor, and in this case this would be 0, and or if we use this model with latent variable, which is like a variation of variational autoencoder, it would correspond to this scale divergence term. So that's not new. We already saw this variational autoencoders, how they work. So that should be familiar. So here, what we have, we get from our data loader inputs, actions, and targets. And we take those inputs here, and we feed those inputs to the model. And also we have this Z dropout, which we will look later. Why is it needed? But for now, and our model outputs the prediction and the loss for regularization term, if we have one. Okay, and so then we compute a loss in kind of, here we have like targets and prediction, and we compute the supervised loss, which is MSE loss for two components, images and like the state. And then we sum this loss and get the loss. And then we do regular backward, like single step of the optimizer, loss.backward, and then optimizer step. And we have some checks to make sure that we don't have nonce here, because like there is a comment here stating that variational autoencoder can output none in some cases, and we want to check for it. And basically that's it. So that's our training. And yeah, evaluation is very similar. So that's our standard supervised training of variational autoencoder, or maybe just predictor decoder. And let's look at this two variants of models we can. Yeah, basically let's first just to make it all like clear. Here is loss computation. It takes basically, we have two components which is target images, target states, and predicted images, predicted states. And we compute like two parts, two components of this loss using mean squared error. So that's really simple, right? And here are two possible variants of the model. One is forward CNN, and another one is called forward CNN underscore VAE. Okay, let's go to that. Here is a simple forward CNN. So that corresponds to the first image without this latent variable. And here we have an encoder and decoder. And encoder here it's just some kind of convolutional neural net. Here you can see that basically it's a very simple convolutional neural net. It has 1, 2, 3 layers and dropouts and leakage. So nothing really special here, right? So yeah, pretty straightforward thing. And yeah, and there are kind of basically this encoder class, which is for some reason named with not a capital letter. I don't know why, but whatever. It outputs it can output different kinds of this decoder for different situations. And but all the decoders basically are some kind of convolutional net, which goes from some number of input channels to some number of feature maps, and then like we have 3 or 4 layers of these convolutions, and that's our encoder. Okay. Yeah, so let's get back to.
Plus, I will like to add the dropout masks that have been applied here.
Yeah. So I think we will get to discussing these dropouts when we get to actually this. Yeah, that's a really interesting part. How they use dropout to do this uncertainty regularization, and we will go into details here. But yeah, that's a good point that you get to notice that we have a dropout for each layer. We have a dropout with yeah, some probability here.
Mm-hmm.
So
yeah.
And yeah, in the paper they mentioned that the probability, the dropout probability was 0.1 here, but you can see that we have a dropout for each layer, right? So that's it. Okay. So let's find that forward CNN back. Right. So that's forward CNN, and here we have like this encoder and decoder. Okay, we had this decoder back here, and decoder is basically mirroring that encoder by doing up convolution. Let me just scroll to it. Yeah, here decoder, it use conv transpose 2D. Again, by doing that, we go back to the original dimensions we had inputted to the encoder. So encoder will like do this reduce the dimensionality of the image, and then we have this up convolutions or transpose convolution as we go back to the original shape of the image, right? Okay. So that's an encoder, and also we have this A encoder, which is action encoder, and that's a linear network here, and it also encodes the action to some kind of hidden state. Okay, and they have an option here to use this U network. And if you are familiar with this kind of how it's, I don't remember how it's called, but that's like really popular architecture used for like some kind of
unit
coloring images. Let me find it here.
Are you talking about skip connections in
Yeah,
unit?
UNet.
Okay.
So they have like an option here to use a UNet.
Okay.
So that was somewhere here, but yeah, let's just skip it because he doesn't mention it in the lecture, and in the paper probably they didn't really use it because they want to have this like separate encoder and decoder here, because they actually want to turn it into a variational autoencoder. Okay, and yeah, so now we should also like notice here that basically this operates as some kind of with this repetitive structure, so as some kind of recurrent network. So we do unroll through these timestamps. So the gradients will travel for basically through all the time steps, and we can have like a multiple time steps here. So there is like a forward single step method, which does all this stuff, uses encoder, and then kind of reshapes it, and then again it uses action encoder. Then we sum action and state encodings, and then we yeah, here you can see that potentially we can use this UNet to add this skip connections. Basically, those skip connections, we yeah, I don't think we like need to go into details of that. Okay, so basically, then we feed this hidden state to the decoder and get this predictions for image and state. So that's basically like as simple as that picture showed, and then we can do it multiple times here. So basically we will iterate through like number of prediction steps, and apply the same thing basically. So we get this encoding and then like do this iteratively, and we like concatenate here. You can see that we concatenate the prediction to the end of the input images and input state. So we kind of accumulate each time step and concatenate all the predictions. Okay. So, and now let's look at the variational autoencoder variant of it, which uses this latent variable. Okay, so here we have this Z network, which would do basically you can see that they use sequential of linear layers with dropouts and leaky release, again to make this Z network. And we have this reparameterize method, as we saw in the variational autoencoder lecture. So probably we don't need to revisit that, but this is exactly the same as it was for conventional variational autoencoder. We had it in the details in one of the previous classes. And yeah, we have a method to sample from this distribution. And there are two modes basically of sampling. We will just the next thing we will consider here. And here is this forward step. And the difference here basically is that we also add this z exp, which is expanded z to match the dimensionality of hidden state of our hidden state. Yeah, so here you can see that we have this z expander, which takes z and outputs a variable which matches the hidden state here. Okay, and in all other regards, it is pretty similar to the deterministic decoder, but we add this like a bit which is kind of variational of the autoencoder part of it. And now we will look a bit more into, let's get back to the presentation and consider one problem this all this architecture introduces. So here we have this, basically to get this variable z, we use an actual next state. Or maybe first, do you have any questions about the architectures we considered before? Okay, so to construct this variable z, we use actual next state observed like in the real world, and this introduces an information leakage, right? So the information can be information about actual next state is encoded into z, this latent variable, and it can be used to predict to formulate the prediction. And yeah, on one hand, we kind of wanted to resolve the ambiguity of the possible next state, but this results in a fact that we ignore the action, because we can infer all the information about the next state from the hidden variable, and in this way, the action is less kind of becomes less relevant. The information provided by action actually is also present in the actual next state, and it turns out it's kind of easier to get this information from z variables than from action, and in this results that the model we have mostly ignores the action input, and that's definitely not what we want. So we have to deal somehow with this information leakage. And how do, okay, now let's check again this visualization here. So probably, yeah, so action sensitivity. Okay, I think this should be it. Okay. Yeah. So and actually, what he is talking about here, that they compare a bunch of inputs, one with real like real z variable and real action, and another one with like sampled z variable and real action, and yet another with like real z variable and like predicted or simulated actions, and basically, or zero action, I don't remember it, but what it results in that the model basically ignores the actions and uses the latent variable z to predict the next state. Okay, And how can we resolve it? So to eliminate this problem, they use what they call latent dropout. So latent dropout, sometimes we will use this. So during training, we like a fraction of times we use this, we sample from the posterior, but sometimes we sample from the prior distribution. So our prior distribution is basically some kind of normal distribution with like diagonal covariance matrix. And by doing this, we kind of randomly use either samples from the posterior distribution or from the prior distribution. And in this way, the network cannot rely on Z variable to predict the next state. So it got to use action to actually output the predictions. And in this way, we can make the network to use the actions to generate the actual predictions here. So yeah, again, so this maybe we have this animation here, I guess.
Yep. And the last one, I think so. The
last one
stochastic
here, right?
forward. Yeah. Yep. The action sensitivity.
Yeah.
Have.
So basically, what we got from it is that by using this latent dropout, we can force the network to actually use the actions to produce the predictions rather than use the latent variable to produce the predictions, right? Okay. And again, let's have a look at the code here. So what's going on here? So sometimes we sometimes we encode the target to Z, or in other cases we just can we can sample Z from some kind of prior distribution, and in that case we don't have all this component, like we don't have the P loss, which is KL divergence component of the loss, right? But yeah, so in this case we sample from just from the prior distribution, and in this case we sample from the posterior distribution, which is built using the actual target image. Okay. Yeah, so let's move on to what we got next. So, okay, we got this model. Now let's try to train an agent here. So the agent is trained with a task cost. And the task cost is, as we discussed about the lane cost plus this proximity cost. All right, and so basically the agent model here denoted by pi, which stands for policy. It takes a state. Here it's position, velocity, and image again, and outputs acceleration and steering. So two components. So the acceleration and steering. And That's our agent. And how would we train it? Okay, so we have this policy network. We have some previous states. So this is a history of states. And we input these states to the policy network and the model, like forward model. And policy network outputs an action. We feed this action to the world model. And also we sample from this. So this is not trained here. This is learned distribution, and the world model is already trained and frozen. So we just use it to train the policy network now. And the world model outputs the next state, and we add this next state, input it to the input to the policy network, and again output the next action and repeat it like multiple times. And at each time step, we compute the loss associated with this state. So as you remember, the state is kind of our position, our velocity, and the image which describes our surrounding. And we can use that previously described loss function to compute proximity and line cost component. And that's our loss. And then we have, we compute this loss at each time step. And then we backpropagate it through all these time steps. So this is basically, you can kind of view it to be very similar to unrolled version of recurrent model, right? And we have all this kind of backpropagation through all the timestamps. So we have a backpropagation through time. In this way, the final cost is incorporated not only into the update which is associated with the last step, but it is like backpropagated to all the timestamp steps. So if our action here resulted in bad cost here, we are supposed to get some gradient feedback through all the model, right? So that's our learning. Again, it's kind of regular supervised learning, but with this combination of policy and world networks. And we have this unrolling through time. And this doesn't work. So that's like a long introduction to something that doesn't work. So here you can see the trajectories resulting from this policy learned in this way. And the trajectories, what do? They try to just get away from the road, because our loss function is not defined outside the road, so no cars outside the road. So probably we get to the place where there is no cars, and in this way we minimize the proximity cost once and for all. So yeah, that's a smart policy, but not very useful in the real world, right? And how can we solve this? So one solution is imitation learning. So here we modify our cost in the following way. We add this expert regularization component. So and what it stands for? So we input some actual actions. So if you remember, we had those actual actions. We reverse engineered those from the observation, from the video frames, and we can use those. So this would be basically data of real drivers we are using here. And this is imitation learning. It's on its own really kind of big topic here, and it has its own limitations. But in this case, it works because we trying to solve this kind of constraint problem where we like operate in a very well-defined environment. And one nuance here that with imitation learning, it actually worked better when we didn't have this latent variable. So it worked better with this uncertain deterministic word model, which outputs a probability distribution of possible next states rather than some some actual possible one of the possible next states. Okay, and yeah, so Alfonso didn't look very very enthusiastic about this. So but as you can see here, it works. So this yellow trajectories here are obtained from imitation learning, and you can see that those are really reasonable trajectories we are driving on the road. But what else can we do? And this is really one interesting part of this paper and of their approach. We can so basically what this kind of behavior can be called, it can be called like we are falling from data manifold, right? So we are going away from data manifold, and we can add so in this case, expert acted as data manifold attractor. And what can we do? We can replace an expert by some like imitation learning from expert by adding some other data manifold attractor, and in this case, this would be an uncertainty regularizer. Okay, so I guess we got to the final kind of words of the name of the paper, and okay, let's consider what we got here. So this is kind of our value, or not a value, our cost fun or action, yeah, right, like real actions here, and this is basically our data. Where we have like data points here. So we what the problem is like here and here, that we don't have really any input, like we don't have any data for this situation outside of the road. Because no real driver ever drove, went outside of the road, and the model did not observe it, and we do not like. Also, our cost function is designed in a way that it doesn't account for possibility to go from the road, right? Except that we have some penalty for not following the lane, but it also is not designed to work outside of the road. Right? So basically all our data and our basically our known interval is within this this is kind of interval where we observe data and where we trained our model. And this interval is where we don't have any observations, and we have no data, right? And what's the difference between predictions within the data manifold and outside of data manifold? And the difference is that the predictions are very inconsistent between different models outside of data manifold. And if you remember it from one of the first lectures, we briefly discussed it, that actually we basically from deep neural networks and any kind of machine learning in general, in general case, we have we cannot rely on the predictions outside of our training data. Yeah, so we cannot use our network to predict on data out of distribution. And here we're gonna use this fact to add uncertainty regularizer. All right, so let's see how it's done. So basically, if you remember the MC dropout trick, basically we have a bunch of dropouts in our model, as Mayank usefully pointed to, like noticed in the code. We have this dropout, and if we do the prediction with active dropout, like usually when we call like model.eval, the dropout is turned off. So we do 0 dropout because we want to get like the best possible, most certain prediction. But if we keep the dropout on, we can basically view our single model as an ensemble of different models, right? So with each different possible dropout mask, we use different neurons of our model, and in this way we have like naturally we obtain this kind of ensemble of the models, right? And we can use the output from these different models to get our uncertainty estimate. And this uncertainty estimate basically is like a variance of our predictions, right? So here the variance is very low because the predictions are very similar between different models. And here the predictions are, the variance is very high because different models predict different, totally different things. And yeah, so by using this variance as estimate of the uncertainty of our model, we can add it to our cost to like in this way. So here we have like regular task cost, right? And also we have this uncertainty cost. So we train our, what it results basically to, that we train our policy network not to drive into the region where our world model outputs are uncertain, right? And those are uncertain outside of our observed data distribution. Okay, so and this is our like final training framework. We have this task cost and uncertainty cost in a total loss, and again we use latent variables to train our model as shown here, right? So we to our world model, it takes like history of states, latent variable, and action, and outputs like this predicted state one that we use, and we use it like we obtain it from the full model, we can call it. And also we have this like ensemble of models with dropout, which output like different predictions, and we use those to get basically to get this cost, which corresponds to a signal which shows us whether we are inside our certainty interval or not. So that's really interesting. And here are some policies obtained from this last configuration, and you can see that these are much more reasonable compared to the blue ones. But also it's from this picture, it's hard to tell if this is better than imitation learning or not. But they have some results in their paper stating that they observed the best performance. Yeah, let me find the results. So yeah, they have this model-based policy with uncertainty regularizer and three variants of it, and model-based policy with expert regularizer. And in two cases, they use this deterministic predictor decoder, and in two cases we have this stochastic predictor decoder, and finally we have stochastic predictor decoder with dropout, with latent dropout, and that is the best. The blue line here, it's the best performing model. Okay, so so what next? Next we have the evaluation, and okay, so we got to the end, and for evaluation we probably have another nice animation here. I hope. Stochastic model with Z dropout. Okay, no, not here is no. Oh, I think these animations correspond to the latent dropout. Okay, so here you can see that we have a model, yeah, but still it's better to watch it in the video because we don't really see the notation here, and it's kind of a bit harder to interpret it without notation. Basically, one corresponds to the real latent variable and real action. One corresponds to real latent variable and some arbitrary action, and other correspond to some actions. Okay.
Yep. There are three basically versions of the predictions that we have got here. So one was the learned policies that you had shown earlier, which had the white dot that was being placed. If you kind of zoom in on the learned policies, a part of the
so where is it?
Just above it, I think so.
Okay, stochastic. Okay, so these are animations of the. Let me. So these are animations of learned policies, right? Oh no, that's action sensitivity part.
No.
So
If you zoom out, then you might be able to better see it.
So,
and then scroll up.
Yep.
Yeah. So this was if we zoom in here, you can see.
Yeah, so I cannot zoom in on the animations. The animations remain of the same size.
No, we can. If you zoom in a bit.
Yeah, I don't get bigger animations. I just get bigger text here.
I have zoomed in 250%. Okay.
Yeah, maybe you can just share a screen for some time and show what if you can zoom in it nicely. I will stop sharing.
Cool.
And you can show.
Just give a brief presentation. I was looking at.
Okay.
So this is the prediction result. So if you guys can see, yeah, this is the predictions based on the 40 and the 200 time steps in the future, and it's the if we can see the ground truth, the deterministic, and the two stochastic versions. This was with respect to the blurriness, I think so, that it produced. Then this was the same. This was the same. Then the learned policies that were evaluated based on the 10 random trajectories from the test set, and you can see the white dot that represents the distributions here. That kind of tries to predict our policy network, our actions that are outputted from the policy network. So it is more like a ego motion. If you have read or are comfortable with the recent research in this field, uh, it's trying to give you the acceleration. Uh, if the white dot is here, suppose, if you guys can see my cursor, uh, if it moves forward, then you're trying to accelerate. If it moves backward, then you're trying to decelerate. And left and right, then it's trying to move or change the lanes. So this is a kind of an ego motion that we can see. So this is what it's being, what it, is being predicted here based on the actions. And uh, uh, this is another example of it based on this. So, and we can see the parameters too in the bottom, the x, dx, the c, and the a. So these are all the parameters that we discussed upon. Then there was an action sensitivity that I think so here they use Gaussian. Yep. The key modification was to change the posterior distribution from a single Gaussian to a mixture of two Gaussians, where one component is affixed to the prior. And this had the implication of uh, input states and actions. So we had two, and we were trying to categorize or disentangle the actions from the other stuff. That's the acceleration, deceleration, and the left and right. Then we refer to as the Z dropout. Uh, uh, Sample Z, inferred Z, true A, and a sample A. So these had four different meanings, as you guys have seen here. So this was, yeah, this kind of a representation that we had. Sampled Z to true A, inferred Z sample A, and sampled Z based on sample A. So yeah, this was this. It's pretty much easy, straightforward, that we had already discussed. And then with the Z dropout, that's the winner here with the stochastic policies and the dropout. So yeah, this was the presentation. That. Yeah, thanks. I'll stop the share now. You can take over. Art. You are muted right now, Otto.
Okay, now, yeah. So I was saying that we can look a bit more on some code. So there are like training functions for different kinds of approaches they used. So here is a training script for expert like expert regularization, right? And we can like look through the code here. So what would our cost be in this case? And again, it's we are using like very simple components here, but that like total picture is like turns out to be interesting. And yeah, so we have a bunch of costs, and here again the training function is really very simple. We get those inputs and actions, and here is like a training step for the policy. So it would iterate over a number of time steps, and like basically perform what we usually like what we kind of consider before. And it kind of takes the input states and images, encodes it into some hidden representation, and if we have like depending on a type of a model we have, we encode this. We get this z variable here, and yeah, so we sample a z variable here, and then we kind of form this combined hidden state if we get this variable z. And then we have an action encoding. So basically, as you remember, the action is actually kind of a tuple of two values. So the acceleration and steering. And we want to like get some representation of it. And like, as you can see, is that all variables are mapped into the same like to the tensors of the same shape. And once again, we have this U network here, which basically introduces the skip connections from like connecting their like convolutional maps of the same height and width, right? So it's easier to reconstruct the image if you can like not only take input from this the lowest, the most kind of squeezed representation, right? But if you can also have a connection to the original image. Right, and that's what your network does. And then we have this decoder, or maybe it's not exactly what your network does in their case.
No,
I don't know.
yeah. That's what I was a bit skeptical about. And if you look at the paper, there is a section which gives U network based on the certainty that cost has been
Okay. So I
applied.
totally misinterpreted it. Because sorry for that. I think he didn't mention it in the lecture, but yeah, let's check the code for this U network, and we will see what it does. Yeah, it's definitely not UNet, because it just produces something which is added to the hidden state, right? So that's not what I said. Okay, so
Yep.
yeah.
If we go to the research paper on the page number 3 or 4, the formulation is given, so it will help in.
Okay, let's check the. So can you see my screen now, or you see just that VS Code?
We just see the VS Code.
Okay, I will share. Go back to the.
I think you
desktop.
had it, yeah.
Yeah, yeah. I will switch to the paper. And which page you say?
Page number 4.
Okay. Let's get to the page number 4. Oh, yeah. Here we got it. So. Okay. All right. This is an uncertainty regularizer we have here, right? So it just combines this basically difference between like kind of difference between this L2 norm of the difference between predicted states, and this would produce the measure of uncertainty. But is that unit? So, does it correspond to what we had in the code?
Yep, I think so, because it is with the uncertainty
yeah. So here is
regularization
a model
feature.
uncertainty cost, right?
Yep.
So basically, that what we talked about. Here we have these predictions from the network with dropout, and we have a bunch of these predictions, and even depending on how different these predictions are, we have this uncertainty cost. And yeah, so basically they introduce it to they encode it in some way and add it to the hidden state of the network, right? Do you think that's what's happening here?
Yep.
With this unit? Okay, might be. All right, so let's maybe check what it takes and what it outputs. Okay, so your network is something we have here, and so it takes the hidden state, does something to it, and we add it back to hidden state. So basically, that what it is, huh? So I'm not sure if it's uncertainty regularizer as well.
There is a on line number 87. There's a class u underscore network on.
Yeah. We just
line
looked at it.
87.
I just.
That's the definition that has the forward and the init methods. So
yeah. So basically, it takes a hidden state, passes it through convolution, dropout, leaker convolution, and it has a decoder. So what's going on here? It takes a hidden state, passes it through encoder, which is convolutional network, then passes it through the fully connected network, right? And kind of reshapes it and passes through fully connected network, then again reshapes it and passes it through the decoder. So basically it just some kind of added computation here.
Yep. That's what the model uncertainty cost is. I think so. What is the underlying objective the policy is trying to learn? I don't know if that is the exact thing, because it's being passed on here, and if we look at it, the features that how do I say it? The gradients that will be back propagated here are being limited in the training function. If we go down to the objective of our loop, so
here is a training script for the this MPUR, so which is with uncertainty regularizer, and let's find this the loss, where the loss is computed here, and
I think so. It is
so bread policy here. Here it's bread proximity. Okay, so this outputted by this function here. Okay, and this function here changes input status size. Okay, it gets the loss action spread states and updates.
Yep, it's on the line number 494. I hope
494. Okay, let's get to
forward CNN if we look at that class.
Okay, here. Let's get to so forward CNN and 494. Yeah, that's where we load this network. So where we get it basically. But basically what it does here, as you can see, it takes your hidden state, does some computation to it, and just outputs something that we add to our hidden state, right? So I don't think that this is uncertainty regularizer. It just operates on a single hidden state we have inside our forward model. So so this new network is just some kind of added computation, which is used probably to increase the expressivity of the network, I guess.
Yep. Even because they haven't given detailed documentation. I think so. There might be some. I don't know, but yeah, you're.
Yeah. Yeah, so I don't think that's really so the architecture itself is not really very important. So what I think is really interesting about all this stuff is this kind of approach to get the estimate of the uncertainty of the model predictions and add it as a and use it as a regularization cost to train the policy network. That was really smart. And also, I think there is kind of a lot of possible applications for this kind of stuff, right? So there are many different scenarios when we want to get this uncertainty regularization. And also what is really, I was just looking through the open review comments for the paper, and basically they added this latent dropout after they had some comments mentioning that we didn't know why you don't observe any so originally they didn't have any improvement using or much improvement using latent variable, over the deterministic predictor decoder. And basically they kind of got this reviews on OpenReview and reiterated on that and came up with better model. So they introduced this latent dropout and managed to get better results. So that's pretty pretty interesting about like stuff you can find in like back in the history of this paper. So yeah, and on the other hand, like it's kind of interesting paper, but also it doesn't look like this is something anywhere close to what you can like get into production or something. It's really kind of conceptual exploratory work, I guess.
Yep, totally agree. Because they have had a parallel evaluation in the GitHub page, and they say that they have tried this with I think so. They have tried to scale it with respect to 10 processors. So I think so. The CPU had gone from 10 to 64 cores, and the number of GPUs to 18 per user, and therefore currently there was a limit to using, I think so, three that is totally dependent on the number of GPUs that are available. So that's the kind of a bottleneck that they are currently facing. So yeah.
Yeah, and I guess to get like really like something evaluate this model in some conditions closer to real world scenarios, you got to get much more diverse set of possible conditions. Like they took these videos from the very similar driving traffic, and yeah, and they like really did some smart stuff with that, but that's really far from what like actual autonomous driving will look like, right?
Yep. And plus, there are some notebooks too. If you guys have tried that,
So
the visualizations and the loss designs.
yeah, I've looked at the notebooks a bit, but I think those are more like exploratory notebooks. So
Yep.
what they use during the development. Yeah.
That gives a very good intuitive explanation as to how they reached to the result that they got. So yeah, that was a insight that I would love to explore. Yeah.
Yeah, I agree. It's kind of cool that they use their own research to like to show at the lectures, and that's really kind of exposes the research process, and also kind of connects the dots. So here is kind of a real application of latent variable models, and like really very concrete demonstration why it can be useful, and when it can be not very useful. And yeah, so probably this like a practical example of applications of the concepts we learned so far. is a good addition to the
Yeah.
theory part we had here.
And plus the transformation, the pre-processing of the images of the traffic to the representation in which they had those state action pairs with the image set and the that was the variable that I am not able to recall, that had the other tensor with respect to the acceleration, the deceleration, the left and the right, and that was cool too, because representing uh, uh, image from that crude data set to a particular environment takes a lot of uh, so yeah, that was one highlight for me too.
Yeah, and they have all scripts, and you can try to use it and like basically look at into the code. Like everything is like nicely written and reasonably well documented, so you can dig into this stuff and try to re-implement it or adopt it to your needs if you have something similar. So okay, so if there are no comments or questions, that's all I had. So
Yep, totally agree. I would like to highlight a similar work by David too, world models. And that was based on the ES strategy. So that I had gone in depth with that too. Yeah, world models. If you guys search it, you will easily find worldmodels.github.io. I will share it in the chat too.
I have a quick comment slash question about world model. So I just wanted to get like an intuitive explanation of what this world model is learning. So is it fair to say that what it's trying to learn is, so if my car is moving at a certain acceleration at a point of time, how do the other cars react to that particular action? Is that what it trying to? Is that what it's trying to learn?
oh, well, I'm not sure if we can kind of formulate it this way. Basically, what it does, it maps like actual actions taken by a certain car into the next state, and basically, yes, it would learn to represent the reaction of the cars. Into like to your actions, but not kind of explicitly, because we don't have like a lot of it's not like we learn to output different pictures for different actions in the same situation, but rather like if you look at it in a global way, right? So we have like current state and our actions, and then this network learns to predict both our next state, which is our next new position and our new velocity, and also new positions of all our surrounding car relative to us, right?
Hmm. So it's like a kinematic model of my car and like how other cars react. But like you said, yeah, there are some problems with that as well, right?
Yeah, but it kind of it doesn't have like kind of explicit model of the other cars. Basically, other cars act like a decoration around us, but because these actions taken by other cars are actually contained in this data set we use. All this is kind of learned by the model, I guess.
Yeah, but I feel like that is what it's trying to learn, right? Even though it's not perfect.
Yeah, I guess it's not perfect, but basically, as we see with that demonstration of different like different possible futures for different latent variables, it learned to predict the behavior of other cars like quite reasonably well. So we observed kind of different basically behaviors for different cars, and in some cases it went kind of faster or slower, but in all cases it was plausible behavior. And kind of one problem with it, and he kind of mentions it in the lessons, that when we evaluate our policy, the other cars are blind to us. So we act we evaluate our policy inside this like inside the environment, which was like an actual environment, but we take different actions, but at evaluation time we have this history replay that the cars are acting as they did as we acted like we did in reality, but we take different actions and car still do what they did. They don't care about us. They are blind to our like simulated car, and our car, like our agent, got to adjust to that. But in real world autonomous driving, actually like modeling these interactions between different drivers, it's like one of their really important and complicated problems, because there is kind of game theoretic component to it. You can like in different situations you can behave more aggressively or less aggressively, and basically your agent got to learn that. And yeah, I'm not sure if this kind of setting like fully like incorporates all this complexity. Yeah, so at evaluation time, those other cars, they do not care about us much.
Yep. We are only concerned about the ego motion of our vehicle with respect to whatever the environment we are in. So, if you guess about the modalities, we only have a top-down view of it. But in the real-world environment, we might have I don't know, minimum 20 or 10 sensors that are available to a car, and based on that we will have to uh, evaluate our policy to get our next distribution, next action in our distribution. So yeah, that will have some sort of a impact on the basis of how can we uh, uh, perceive our environment based on the sensory inputs that we have. So that's one practical consideration to take care of. But other than that, our environment is not being modeled. We are just kind of inserting those stochastic, how do I say it, uh, 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 noise in our distribution to get the next, as I've alluded to earlier. Yeah, that was from us.
Okay, I guess we are running out of time. And if there is no more questions, we got to wrap up.
Okay, thanks, Arto. This was very, very interesting.
Yeah,
Thanks,
thanks everybody for your attention.
Okay, bye bye. And for the next 2 weeks, we'll have NLP. Yeah.
Yeah, cool.
Okay, bye bye. Thanks, everyone.
Thanks, guys. Take care.